Guess we can't wait forever. And presuming, as usual, you people can hear me out there. And so,
Yes, sir, we can hear you.
yeah, thank you. So I will start where we left off yesterday. Yesterday we had a sum of, at the last, as we ran out of time, which is example 8 on page 752. And what we're going to find out, if we haven't already, is a lot of series of numbers that we are looking at will have a sum. In other words, the limit of the sequence of partial sums will have a limit, but we might not possess the ability to find out what it is. So we will have methods to prove it converges to something, but we might not know how to find that. And the rest of the part of the rest of the chapter has to do with ways to try to find such things. Anyway, there are a couple of types of series for which you can always find the sum. One of them is geometric. And there are rules for a geometric series will sometimes converge and sometimes diverge. It has to do with the size of what's called the common ratio, or the letter R, that we used in the geometric series. In geometric series, we had a letter A and a letter R. The letter R was the thing that had the power attached to it, and that's called the common ratio. If the common ratio in absolute value is less than 1, then the series converges. So, geometric series are, in geometric series are ones for which we can determine the limit of the sequence of partial sums. There's another kind of series for which we can always determine whether it exists or not, and that's called telescoping series. Now, I didn't get a chance to explain why it's called telescoping yesterday because we ran out of time. Telescoping series are ones that look like partial fractions. In other words, when you're doing integrals, we have now things called partial fractions. And when I look at this 1 over k times k plus 1, that's something because it's a product of two things that I can change into the sum of two things. And that's what kind of series, if you see this kind is going to have a sum that we can find. So what do? You treat this as if we would treat, this is not the integral 1 over x times x plus 1, but what you do to the integral 1 over x plus 1 and what we do to 1 over k times k plus 1 is the same thing. We're trying to find a and b for which we can replace this 1 over a product by the sum of two things. Okay, so you already know about that. You know how to do it supposedly. And so I just did it for you here. You make a common denominator and there's various things to do. This is one way. In this particular case, I collected the coefficients of k and the constant. That's set identically equal to 1. And that means the coefficient of k is 0. That means a plus b is 0. And the a is equal to 1. And so if a plus b is 0, b is minus 1. And so we can divide the 1 over k times k plus 1 into the difference of 1 over k and 1 over k plus 1. Now, once you have that, we no longer worry about the infinity here. We look at the partial sums. The key to doing this is to look at the partial sums because it's the limit of the partial sums And later on, when we get to here, if I can find out what the partial sums are and take their limit, that's how you do it every single time with this stuff. So what I want to do is write it out. Well, a finite sum of two things I can write as the sum of each of them. Okay? Finite sum, not an infinite sum. But if it's finite, this says I can add all these up first. You know, if you've got a bunch of numbers to add up, and it's like 1 minus 5 plus 6 minus 2 plus 7 minus 4. You can, if you want, add up all the pluses and add up all the minuses and take that arithmetic later. That's all I'm doing. The sum of all of these is the sum of these minus the sum of those. And that's 1 to n, 1 to n. In one case, I have 1 over k. In the other case, I have 1 over k plus 1. It's my opinion that you should do this example yourself because you need to see how this stuff works. There's some subtleties about it. And right now we have k from 1 to n. I use k instead of n because I like to sum, I like to get the partial sum with n. So I use k's, as I said yesterday. The book uses 1 over n times n plus 1. Same thing, except then he's got to do something else for the partial sums. I prefer to have the partial sums be s sub n, can be anything else. Anyway, so up here, we have this difference. And what I'm going to do, from down here, I have k plus 1 in the denominator. I'd like to have k's all the time. So in order to change the second series, finite series over here, right now it's from 1 to n of k plus 1 in the denominator. I'd like to change this k plus 1 to k. That means I want to change this subscript by moving it down 1 here. So instead of k plus 1, it becomes k. When you change the meaning of the subscript down 1 here, you have to up it here by 1. So what happens over here is what used to be 1 to n is now 2 to n plus 1. That's one of the subtleties that you have to get used to. When I've done that, now I have 1 over k. When I look at this, I have k from 1 to n, 1 over k, and k to 2 to n plus 1, 1 over k. So if k was 10, for example, I'd have 1 plus a half plus a third all the way to 1/10. Here I'd have 1/2 all the way to 1/11. So there's some of them are the same. And that some of them the same is why we call it telescoping. And the idea of telescoping has to do with maybe you've seen people in ships and stuff in old days, like movies where they extend a telescope out. The telescope will be long and then they collapse it. That's what telescoping means in this case, is it's collapsible, meaning you have a long thing here, and what's going to happen is I'm going to split off k equals 1 here, and that's 1 over 1. And then I'm left with 2, because I just took 1 off. The first one in the sum I split off, I'm left with 2 to n. In this one, I'm going to split off the last one. So in this sum is 2 to n, and then you'll notice that this is going to disappear. That's why we call it telescoping, because it collapses. What's it collapse down to? 1 over n plus 1. 1 minus 1 over n plus 1. So the series is the limit of this thing right here, and that's now easy. It's no longer a sum, it's just this, and literally you know what that goes to 0. So this series adds up to 1, and what we write at the end is equals 1. So we use this symbol for both the question and the answer if there is an answer. This particular series converges to 1. So when you have products like this, we have telescoping series. And I'm going to come back to that in a little bit. There's a couple of things in the book to talk about next. And one of them has to do with looking at a series. And when you do that, this series is a sequence of partial sums. That's 1 to n. Okay. Keep trying to make sure we have people who wish to come in. If you guys is joining us, I've been going over example 1 on page 752. I started today and I've already talked about this board, which is to go through the example on 752. So you can read the text in 752, or you can look at this now or later on the video, and it continues over here. So this, as far as people just coming in, we start here. This business up here is not relevant to what I will have you remember. Anyway, this is thing, and this is the end of it. And so this is the end of section 1. And I'm just now starting to talk about a series in general. Okay, so the partial sums are just adding from 1 to n. If n is 10, it's a1 plus a2 and so on to a10. And the partial sums here are interesting. And if I would subtract one partial sum from the previous one, I would just get an. Okay, remember that S1 is A1, S2 is S1 plus A2. So if I subtract S1 from S2, I just get A2. And if you subtract Sn from Sn, or Sn minus 1 from Sn, you get An. Now, suppose that this series has a sum. Now, the series, if it has a sum, is the limit of the sequence of partial sums. That's what it is. So let's call this limit L for a minute. So suppose the series has some L. A while ago, I showed this previous example that the series had some 1. So I'm saying the sum I'm calling L. So if that's true, then what happens to Sn as n gets big? It goes to L. What happens to Sn minus 1 when n gets big? It goes to L. So what happens to A sub n as n gets big? Goes to 0. So we have a theorem. Now, I need to erase, so I apologize for everybody who came in late, but you'll have to look at this later if you haven't looked at it hard yet. It's example on 752, as I said. Anyway, if the series converges, then the limit of the A sub n or A sub k's, the terms go to 0. Now, those of you who had me for Calc 1 honors remember we spent a couple of weeks talking about logic. This is a conditional sentence, an if-then sentence. It is logically equivalent to its contrapositive. The contrapositive says if the limit of the sums is not 0, then the series diverges. You remember that when you take a contrapositive, you switch the if and the then, and you put nots on both. So if I said, if you come to class today, then I will give you an A, the contrapositive is, if you didn't get an A, then you didn't come to class. Now, so from this if-then sentence, that if the series converges, then the terms go to 0, we get a divergence test. The divergence test is the contrapositive, logically, of the original if-then sentence. It's the if-then sentence turned around with knots on both parts. So if the terms don't go to 0, then the series diverges. So, for example, from now on, if you just had n here, n from 1 to infinity, 1 plus 2 plus 3 plus 4 plus 5, it doesn't take a genius to think that adds up to something really big because you keep adding and adding. But what we can do is use this divergence test to say, since n does not go to 0 as n gets big, this series diverges. Okay. Now, if you also remember that first couple of weeks in Calc 1, for those of you who were there, the converse of a if-then sentence is not necessarily true. Okay? If I am Bill Gates, then I am rich. If I am rich, then I am Bill Gates. The one would probably be considered to be true, but the other one is not. The converse of a statement has nothing to do in terms of its truth to the original. The contrapositive does, it's equivalent, but the converse is not. And the inverse is not. The inverse is the contrapositive of the converse. Anyway, so what happens to people who aren't paying much attention or who don't study or who are just dumb is that you get this backwards. When you get it backwards, you make the wrong conclusions. So what would the converse of this be? If the terms go to 0, the series converges. No matter what I say, some people will believe that. And that's why you probably take the test again, or maybe the class again later. And I'm smiling because I'm not trying to be mean here. Okay, don't put it in your teacher evaluations. I'm mean. I'm joking. Put in your teacher evaluation, I can't make a good joke, but don't say I'm mean. I am mean, but not for that reason. Anyway, if it converges, the terms go to 0. If the terms go to 0, you don't conclude anything. Okay? What does this one say? If the terms don't go to 0, then it diverges. Yes. If it diverges, then the terms don't go to 0. You can't say that either. You can't turn it around. I mean, you can turn it around, but you can't turn it around and be correct. Okay? Okay, so some series, when you look at them, you can see they diverge immediately. Now, here's a little problem. Here's a series now, 1 over n. We've looked at this one already. This is called harmonic. Does it converge or diverge? It diverges, but the terms go to 0. The terms go to 0, but it diverges. That's an example why the converse of this statement is false. The example here, a harmonic series of terms do go to 0, but the series diverges. So don't conclude if the terms go to 0, it converges. That's the converse, it's wrong. And I hope I've dwelt enough on that this time to convince everybody. The terms going to 0 don't tell you anything about convergence. If they don't go to 0, they tell you about divergence. Try to get that straight. Okay, that's in the book on 753, and he even puts in red at the bottom, note, the converse of this is not true, and so on. So he warned you, if you read the book, it's in red, if you're not colorblind, and you have that test. Okay, so the next page, 1, gives you an example of that, where we have something that happens, and that I'll write that down. So I'm now going to erase this part up here. But the example isn't very exciting. There's some better ones. But anyway, in this one, the example has n squared in the top and 5n squared on the plus 4 on the bottom. N squared and 5n squared plus 4. This is what he has from 1 to infinity, The point is that if you just look at the term, what does the term do itself? This is not the sum of the series. This is the limit of the terms. The series sum is the limit of the partial sums. I'm not doing the limit of the partial sums. I'm doing the limit of the terms. That's totally different. The limit of n squared over 5n squared plus 4. You guys know how to do that. What we do is we divide by n squared, and you get a new limit, 1 over 5 plus 4n squared. What does this do? It converges to 1/5. What can we conclude from that? The terms don't go to 0. Therefore, the series diverges. The terms head toward 1/5. So what this series is like, when the n gets big, it's like adding a fifth plus a fifth plus a fifth plus a fifth forever. And that's not going to converge. That's going to diverge. And while I'm at it, let's talk about one more little idea. A series from 1 to infinity, if I went from 10 to infinity with the same thing, we said this diverges. This will still diverge, right? In other words, if I start with the 10th one, remember it's when n gets big that the numbers get close to 1/5. So a series, if you take off the first finite number of things, I just took off the first 9 things from this sum. If the series converges, it changes the sum, but it doesn't change whether or not it converges. Okay. For example, we've already talked about 1 plus a half plus a fourth plus an eighth, and so on. That converges to 2. A half plus a fourth plus an eighth will also converge, but it converges to 1. If I remove the first number here, I don't change whether or not it has a sum, but I change what the sum is. Okay? So we don't worry so much in a series about if we're interested in convergence or divergence, we don't worry about the first term. We worry about the ones after a while. And after a while in this series, they get close to 1/5. The beginning, I don't care about in terms of convergence. And since this one diverges, I don't care about them at all. On the other hand, if I have a series like this, and I know it converges, and I do care about where we start. Because I'm interested in the sum and what the sum is, then I'm interested in which terms we have and which terms we don't have. But if I'm only interested in convergence, I don't care about the first 10 or first 1,000 terms. I care about what happens when n gets large. Okay? So, okay, now, the next thing, and really the last thing as far as the section goes, not the exercises, we're going to do some exercises, but this section talks about if I have a series, and I told you guys yesterday, about the test. When you have something like this, if I have a series and I notice that every single term has a number multiplied to it, not added, multiplied, factor, then I can take the factor out and only worry about the series of an, whether it converges or not. If it converges, then if there is a sum, then the answer will be C times the sum. If the series from 1 to infinity of a sub n adds up to s, then the series with C times everything will add up to CS. Okay, and that just comes from limits. As you know, with limits, if you have a constant times something, you take the constant out. Similarly, if I have the sum of two things, if I have, instead of this, if I have an plus bn, I can separate the two things and look at them separately. Okay. If both of them separately converge, then the sum will converge, and the sum of the series will be the sum of the two parts. And that's the latter part of this section, and it gives you an example of that. I think it's pretty easy to understand. You just break it up into two parts. Now, this is when it's added, you break it up. You only break it up when it's multiplied if it's a constant times, not two multiplications of series. That's different. Okay, now, about 9 o'clock this morning, I looked at the exercises, and I started working a few of them myself because I wanted to see a couple of things. It's something, when I see certain problems, they challenge me. Now, I'll explain that in just a minute. Before we do that, yesterday we talked about the Cantor set. Okay? And I wanted to do something with the Cantor set, and then we'll talk about the exercises. And by the way, the Cantor set is an exercise. It's just on the next page. The exercises here start on page 755 and go all the way to 759. So there's lots of exercises about this stuff. Okay, the Cantor set is problem 89 on page 758. So we'll get there. But since I did it yesterday, if I have that thing, if I have this deal and we go back to talking about removing the middle third and so on. So if I talk about what I remove a third, right? And the next time I do it, I'm going to remove the middle third. So what am I removing? I'm removing 2/9 of the interval. And then next time, see, so I'm going to have this left and this left and this left and this left. The next time I remove a middle third, I'll be removing one of those and one of these and one of these. I'll be removing 4 27ths. And I begin to see a pattern. Every time I do this, I get double what I had before. When I do the next one here, I'm going to get 2 more for the one I had. So the next is going to be 8/81. This is the amount of stuff I'm removing. And so the amount of stuff I'm removing is a series. And yesterday we said, suppose we keep doing this forever, whatever that means, what would this amount of stuff? So if I have some land and I go in with a shovel and I take out certain dirt from something, or remove some concrete from a walkway or something, and I keep doing this, and I keep piling this in my truck, the stuff I take out, what does the stuff I take out add up to? Well, if I only stopped here, this adds up to whatever these numbers add up to. But let's look at this a little bit. If I take out a third, I mean, maybe not, don't take that out yet. I see 3, 9, 27, 81. 1, 2, 4, 8. What I see is powers of 2 and powers of 3. 2 9s, 4 27s, but the 2 is 2 to the 1. This is 2 squared, but this is 3 cubed down here. So if you think about this a little bit, 8, when k is 4, 3 to the 4th is 81, and 2 to the 3rd is 8. So I have figured out what we call the general term here each time. So the series I'm talking about is k from 1 to infinity if I keep adding up or taking stuff out forever. Okay. And this is a geometric series. So I know how to add it up. And this was astounding to people in the 19th century, what we're going to do here. So what I'm going to do is try to make this thing a geometric series. And I got to remember how I told you yesterday, there's only two forms. So if I want to do 1 to infinity, I got to make this something to the k minus 1 power. And if you do that, you'll get this series right here. And so this is geometric. A is 1/3 and R is 2/3. And the sum of the series is A over 1 minus R. And that is 1. So the amount of material I remove is 1. Now, what was the amount of material in the whole thing? 1. This was astounding to people because when I talked about the expanding in thirds, remember? All we did was remove all the decimals that had to do with 1, which left all the decimals that had to, they weren't decimals, they're ternary numbers, but all the numbers that had 0s and 2s. And we said yesterday, we still got like 2/3 of those numbers. But the amount of material I remove is the same as the amount of material that's counted in the whole thing. So what is the measure or amount of material that's left in terms of length or in terms of area or in terms of some way of measuring something? So we measure the whole interval by its length. So how much stuff have we got left? It's called measure 0. Because we removed the whole number called the length. Length is 1, and we remove 1 amount of stuff. So if this was 1 yard long and you have that, take that out of your driveway or something, you would be removing 1 yard of stuff. But what we're left with is an infinite number of points. In fact, an uncountable number of points because we only took out 1/3 of them. We still have 2/3 of them left. And so this was as an example of an uncountable set whose measure is 0. And that was considered in 1860 impossible. And when this first was done, nobody believed it. I'm talking about the Einstein types, okay? The people who were not mathematician types wouldn't even ever heard about this, but the people who were trying to define the number system, this is one of the paradoxes. We're trying to talk about integration. What's integration do for us? It gives us area, right? Or it gives us length. And here is an example of something that has 0 length, but is uncountable. And so this was a big problem in the later part of the 19th century because they didn't believe it. And this is why Riemann integration turns out to be not as good a solution to finding area as one would like. Because there's lots of things that Riemann integration doesn't do for us that we would like it to do for us. Okay? That's why around the turn of the century, we had a new kind of integration called Lebesgue. And that's why I told you guys in 1978, we have another new kind that nobody talks about yet in Calc 2 classes. And that's called the gauge integral. It's another better integral, a better way of talking about it. Well, anyway, that's not, has nothing to do with chapter 11.1, but I thought that might be interesting to you about the Cantor set. Now, if we turn to that page, problem 91, and look beyond it to part B in that, part B, problem 89, has to do with Sierpinski's carpet. And Sierpinski is a mathematician, I believe, from Poland. And Sierpinski is an interesting guy in many ways. One is there's some ancient ruins in Ireland that I visited about a year and a half ago before COVID came out. And I was in a tomb from like, I don't know, 2,000 years old tomb of stuff, of old Irish stuff. And the guide in the thing said that there's a mathematician named Sierpinski who's the one who figured all this out inside this tomb. Well, it's the same Sierpinski here as this particular person. And anyway, Sierpinski's carpet is to take a area like a rug and start cutting out holes in the rug and removing pieces of carpet. And if you look at problem 89B, you will see the carpet being removed. And it's very similar to the Cantor set because basically you keep removing smaller and smaller pieces, but more and more pieces. And it turns out, and you can read about it, the Sierpinski carpet, in other words, the parts you take out, what's left with the carpet afterwards has area 0, even though it's, if you look at it, he has a blue carpet here. If you look on the floor, you'd see blue, but the area of what's left is 0. So these are paradoxes, which are only explained when you do the mathematics properly. Okay. Then there's some others. There's a problem in 91 is kind of interesting. In 92, having to do with circles in a triangle. There's a nice triangle in problem 80 about if you had basically inside a triangle, if you had something going up and down inside the triangle, the question is, how far do they travel? Okay, so if you put something in a maze and made them go up and down, what's the total length of that? That's a problem 89, so on, 80. But before we get to that, there's a problem I think we should look at, which is number 64. And this is the kind of thing I hope you do yourself. I would like to not do this for you today so you have a chance to do it yourself. But I'm afraid when you look at the problem, you won't do it. So because of that, I'm going to do it anyway. So the series here we're interested in is the natural log of 1 plus 1 over n, from 1 to infinity. I hope you will find this one interesting. How do you sum it up? Well, the first thing about series is you do not look at them as adding up an infinite number of things. You look at them as the limit of a sequence of partial sums. But right now, I don't know, I mean, I can write a sequence of partial sums. I'm going to change this now to k, not what the book has, but I'm going to change it to k. I hope everybody understands that. So I'm going to do k from 1 to n. That's a sequence of finite sequence. So if n is 5, for example, this would be the log of 1 plus 1, plus log of 1 plus a half, plus log of 1 plus a third, plus log of 1 plus a fourth, plus log of 1 plus a fifth. 5 things. So how would I take a limit of that? Well, I don't know. So what you do here is play with the thing a little bit. What do we know about logs? Well, the log of a sum, you know nothing about. We know about logs of products and logs of quotients. So what I'm going to do is take log of 1 plus 1 over k and rewrite it as log of k plus 1 over k. And that's the log of k plus 1 minus the log of k. So this series is the sum from 1 to n of the log of k plus 1 minus the log of k. Now, why is that interesting? To me, I hope to you, because this is telescoping. Now, This is a telescoping thing, as we're going to see, because I have a difference of things here. What did we do when we did the 1 over n times n plus 1 earlier today? 1 over k times k plus 1. We split it up into the difference of two things, and then you applied this finite sum, not the infinite sum. If you put infinity here, you're wrong, and I will, if you do that later, I will give you 0 on your problem. Anyway, I'm going to write this as the sum n equals, sorry, this should be k. K equals 1 to n of log of k plus 1 minus the sum from 1 to n of log of k. I'm just splitting it up. Finite sum, I can do that. And now I think, hey, I'd like to make this the same stuff, so I'm going to change the meaning of the index down 1, which means I have to up it 1 over here. So, and I want to see if I did it right in a second, so I'm going to check it. Now, if I let k be 2, I get log 2 in this one. If I let k be 1, I get log 2. That's the same. If I let k be n plus 1 in the bottom one, or if I let k be n in the top one, I get the same thing. So these two things I'm going to put a box around are equal. I just changed the meaning of the index. Now, here I have 2 to n plus 1 of log k, and here I have 1 to n of log k. So I notice that I have some of the same stuff. So I'm going to take off the n plus 1. This is going to be log of n plus 1 plus the sum from 2 to n of log k minus the sum of 2 to n of log k minus log 1. I want to take off the first one of these and the n plus first one of these, and I'll be left with a middle, and what I hope you see is the middle, and I hope you can see this at home, the middle drops out. The log of 1 is 0. So what is Sn in this problem? It's the log of n plus 1. No more sums. I have figured out what the nth partial sum is. So what is the sum of the series? It's the limit of Sn. What's the limit of log of n plus 1? Well, since the limit of, as n goes to infinity, of Sn is plus infinity, the series diverges, the original series. And I thought it would be interesting to you guys to see another telescoping series that's different from the other kind of telescoping series. And you only see it collapse if you do the partial sums. Okay? So this is a good problem for you to do yourself. You will understand more things if you do. And that brings me to problems 65 and 66, which for me, I want to talk about that a little bit. 65 and 66, the author says, use your computer algebra system to do these problems by machine, he says. Now, I have written software and sold it commercially. So I am on the side of doing things like that because it made me money, as well as hopefully did some things I couldn't do by myself. Okay, the computer is a wonderful tool, and you can do series on the computer without a piece of it being in your brain. This is how some of you learn trigonometry. Okay, nothing was in the brain, it was all in the machine or something, because you didn't learn it yourself. And I'm not trying to be personal or mean or anything, but you can do every problem in this book if you find the right computer program. And that's because we now have massive amounts of storage capability so that we can do computer things symbolically instead of numerically. Now, the book wants you to do the next two problems by the machine. Okay. Now, for me, as a math person, an old math person who didn't used to have a machine like this would be wonderful if I was 15 years old and had a Pro Mac or something. It'd be great. I'd do everything by hand. Okay. Well, when I look at these things, I think, how did somebody program the sum of a series? Somebody had to figure out how to do this. If I use their expertise, it's like cheating. That's the way I feel about it. I want to know, how do I do it without the machine? That's just me. So I suggest you work these two problems without the computer algebra system, even though I think it's a wonderful idea to have. In other words, can we do these problems? This is what challenges me. At 9:15 this morning, and I have a half hour to get here to drive, 9:15, I decided to work these two problems by hand that the book says do them by computer. Now, I'm not trying to brag about my abilities, it just challenges me. And I hope as honor students, when you see these problems, you don't think, oh, I'll go into my powerful PC to solve this. You ought to first think, I wonder if I can do this myself. And I would suggest you try to do it yourself, because 65 is easy. It's something you can do in 3 lines. There's no reason to ever put it on a computer. But you won't recognize that. I mean, there's some problems where you have to do it because we just humans aren't that good. Okay? Machines, we can work it all out, but the number of steps would take us way too long. And what the computer can do is do things fast. It also can get in trouble fast. But assuming it doesn't get in trouble, it's a wonderful instrument. But I want to look at this first thing here, because I say when I looked at it at 15 minutes, and by 9:25, I had both these problems sort of solved. Okay. And again, I'm not talking a thing about ability here. I'm talking about just being irritated by what the book says that we have to do. And it says he wants us to sum this thing. And so I'm going to write it down here, and we're going to run out of time here, so maybe I won't be able to do this. But it's n squared plus n cubed, n squared plus n cubed. And the book says you guys are not good enough to do this by hand. So you have to do it by machine. That's what he wants you to do. Now, really what he wants you to do is get practice. But I want to do this myself. So the challenge, because it's 18 after, is, so I won't have time to do it here. I contend you can do this problem in about 3 steps, 3 equal signs. Are you that good? Can you guys do it? Okay. Now, I should also tell you in the minute I have left here, I started to do it the way I'm supposed to do it, which is the hard way. Namely, I'll do a little bit of this in this. I see this denominator, I think, hey, that's n times n plus 1 cubed. And so I see the denominator as a partial fraction. So the way I started to do this, because I didn't know when I started to do this, whether or not this was easy to do by hand or impossible. Okay, the author wants you to do it by machine, so maybe it's impossible. So I started this, I thought, hey, this just looks like partial fractions. So let me write down what would be the partial fractions. This is what I actually did in between 9:15 and 9:20, is I wrote this down as A over N plus B over N squared plus C over N cubed plus D over N plus 1 plus E over N plus 1 squared plus F over N plus 1 cubed. This is what I actually wrote down, and I can actually show you guys, this is what I wrote down. It's right here. That's the thing I'm talking about right here. That's what I did until I saw a key to how to do it the smart way. Anyway, I went and tried to figure out what is A, B, C, D, E, and F here, which filled up about half the page, which I can show you. Filled up about half the page, and I started working on it, and then I got smart. Then I found a way to solve this without doing all of this. Okay, so I recommend to you trying to do this by hand. And tomorrow, if I'll show you that this is really just about three or four lines, and you're done. But that means there's something to do with these two things that you can simplify. Okay. Now, the other problem is 65 or 66. I did that also. You have to factor the denominator there. And the denominator is a fifth power polynomial. So that will give you some practice doing synthetic division to find out what the roots are so you can factor it. Okay. So 66 is telescoping. So I challenge you to do those two problems and show me tomorrow. So we're going to stop the recording.